Alright, in today's video we're going to take a quick look at how to do some nomenclature with alkenes and alkynes, two different types of hydrocarbons. Let's begin with some fill-in-the-blanks questions. If you want to try looking at the fill-in-the-blanks and doing it yourself first, that'd be awesome. So the first one, we'll say saturated hydrocarbons include both alkanes, where we have just carbon-carbon single bonds and no rings, and cycloalkanes. Cycloalkanes, as you know, have rings in their molecular structures. All right, so they have the maximum possible number of hydrogen atoms, which is why they are referred to as saturated. On the other hand, unsaturated hydrocarbons will have fewer than the maximum amount of hydrogen because we now have carbon-carbon double bonds. That'll be for alkenes, and triple bonds. A hydrocarbon with one or more double bonds is an alkene. Remember that the name of these molecules will end in ene, E-N-E, where an alkyne will have one or more triple bonds in its molecular structure, and their names will end in Y-N-E, so they'll end in ine. All right, this is a little bit of application of organic chemistry to oil refining. When large alkane molecules are heated to very high temperatures and very high pressures, the molecules break apart and they form smaller alkanes, and they also form ethene gas. Ethene gas would have two carbons and a double bond, alkene, and we'll throw some hydrogens in to give them 4 bonds each, and that would be ethene gas. That process of heating the alkane to high temperatures so that it breaks apart is referred to as thermal cracking, and it's done in oil refineries. It can be done at lower temperatures and pressures, but if so, you need to use a catalyst to make that possible. All right, some nomenclature. We're going to try to name these alkenes, and we'll write the formula down as well, the molecular formula. So we know it's an alkene because we see a double bond in the molecular structure. In the bond line formula, we have a double bond here. Let me just use a different highlighter. So the double bond tells me that we have an alkene. Next, I look at the number of carbon atoms, and we can see that this molecule has 1, 2, 3 carbon atoms. If it were just an alkane, we would call it propane. But because it has that double bond, and it's now an alkene, its name is propene. We don't need to specify where the double bond is because propene has only 2 bonds. Whichever bond was the double bond would be bond number 1 in the molecule, so we can leave out the 1. We don't have to say that the double bond is the first bond because there's only 2 bonds and they're identical. The chemical formula, remember that an alkane would be C3H8. It would be 2 times the carbons plus 2. But to make the double bond, you had to take away 2 hydrogen atoms. So instead of CnH2n plus 2, we now get CnH2n, which is the same general formula as a cycloalkane. So C3H6 would be the molecular formula for propene. You want to prove that to yourself. Look at the middle carbon in the molecule, where there's a carbon here. It currently has 3 bonds, so to give it a 4th bond, you would attach a hydrogen atom. And now if you count your hydrogens, you have 6 hydrogens in total. so C3H6. The second molecule, let's identify the parent chain. It has 1, 2, 3, 4, 5 carbons in the parent chain. So you'd first think of the molecule pentane, but then you see that double bond, and that tells you it's an alkene. So instead of pentane, we're thinking pentene. But we have to go a bit further, because now we have the double bond where it could have been in more than one place. In this molecule, the double bond is the first bond, but it might also have been the second bond in the molecule. If it were the third bond, if we think of the third bond, if that was the double bond, then we would have needed to count from the opposite side of the molecule. You'll start numbering at the end closest to the double bond. So if the third bond from the left were the double bond, then it would actually have been the second bond counting from the right. And we've already dealt with that case. So there's two different kinds of pentene. There's the pentene where the first bond is the double bond, and that's what we have here. And there's the pentene where the second bond is the double bond. So we need to tell which one we have, so we're going to say that this molecule, we'll use the UPAC way of doing it, is pent-2-ene. Whoops, pent-1-ene, isn't it? It's the first bond. That's the double bond. So pent-1-ene. If you're an American student, they do it a little bit differently. The American naming system takes the 1 and puts it in front and calls it 1-pentene. But the correct UPAC way of doing this was to say pent-1-ene. That's the one I'd prefer my students use. The chemical formula with 5 carbons, we follow the general formula CnH2n, so it'll be C5H10. The third example, see if you can do that yourself. Pause the video. So this one here, the parent chain has 1, 2, 3, 4, 5, 6, 7 carbons. And we notice that it's the second bond that is the double bond. The second bond, because we have to count from the end closest to the double bond, so we'd be counting from the right end. This was the first bond, this is the second bond. So we have a heptene, 7-carbon alkene, and the second bond is the double bond, so this is hept-2-ene using UPAC nomenclature, or the American way of doing it, 2-heptene. And then the chemical formula with 7 carbons, it would be C7H14. Now alkenes can also have branches. Example D has a branch. See if you can name that on your own. So to begin with, let's find the parent chain, the longest continuous chain of carbons. 1, 2, 3, 4, 5, 6 carbons. So this is going to be a hexene. And then we notice that the double bond is again the second bond in the molecule. You number from the end closest to the double bond. Once you've done that, you continue numbering from that end for any branches. So this was the second bond, but in terms of carbon atoms, this is the first, let me use a different color here. So this is the first carbon atom, the second carbon atom, the third carbon atom, the fourth carbon atom. So now we can put this together. So carbon 4 has a methyl branch, so we can say 4-methyl. And then the hexene, 6 carbons, but it's the second bond, which is the double bond. So 4-methyl hex 2-ene would be the correct UPAC nomenclature. An American name would say 4-methyl, and then they would say 2-hexene. The chemical formula, it's got 6 carbons in the hexene plus the 1 carbon in the branch, so it has 7 carbons, and just like up above, it'll be C7H14. which means these two molecules, the hept2-ene and the 4-methylhex2-ene, those are structural isomers. They are molecules with the same formula, but they have different structures. They're built differently. So those are structural isomers. Try the fifth example, part E. So the parent chain also needs to include the double bond. So we'll start here and go 1, 2, 3, 4, and you can go either way, 5, 6. So there is 6 carbons again. And notice it's the second bond again, which is the double bond, counting from the end of the molecule closest to the double bond. If we continue counting from that end, carbon 1, carbon 2, carbon 3, carbon 4 has a 2-carbon branch. So this molecule is very similar to the last one, but instead of a methyl branch on the 4th carbon, we now have an ethyl branch. So this guy will be 4-ethyl, and then hex-2-ene. Or if you like the American system, 4-ethyl 2-hexene. Now keep in mind that in my class, I want you to use the UPAC way of naming things, not the American system. Having said that, if I give you an American name, if I said 4-ethyl 2-hexene, I'd expect you to be able to interpret that. But if I ask you to name a molecule in my class, I'd like you to use the UPAC nomenclature system. The chemical formula for this, the hexene has 6 carbons, the ethyl has 2 carbons, so this is C8, and then H16. This is not a structural isomer of the last molecule because it has a different chemical formula. All right, I'll let you finish off that question. Coming down to the third question in this set of worksheets, give the correct UPAC name and formula for the molecule on the left, and this is showing you the molecule using an expanded notation. But it's the same idea as using bond line formulas. Find the parent chain, and this is pretty straightforward. It's got 4 carbons. Okay, and it says that the name given is incorrect. Whoever named this just called it butene. Do you see why that name is insufficient? With 4 carbons, the double bond could have been where it is here, the first bond, or it could have been the second bond in the molecule also. So you have to specify which it is. So the correct name for this would have been but1-ene. Its formula, C4H8. Now keep in mind, if there is no ambiguity, I think we mentioned this earlier, if you had a propane molecule with 3 carbons, so CH3, CH double bond CH2. In this case, you could simply call that propene, okay? Because whichever bond were the double bond, that bond would have been the first bond in the molecule. You'd count from the end closest to the double bond. So with propene, you don't need to say prop1-ene because there's only one type of propene. But with butene, we have 2 different types, so you have to tell me which it is. All right, let's keep going here. Question 5 asks us to draw condensed structural formulas for these molecules. Let me show you how I would do this. So 3-methyl-2-pentene. So 2-pentene, this is the American way of naming it. We'd start with the 5 carbons, and with ene, I can tell there's going to be a double bond. So when I do this, I always draw the double bond first. Then I notice that it's the second bond in a 5-carbon chain, which is the double bond. So with that in mind, I'll put a carbon here. So this is now the second bond in the chain. And now I have 1, 2, 3 carbons so far. So 4 carbons, 5 carbons. There's my pentene, or pent2-ene, I suppose, right? Now the third carbon has a methyl branch. So the third carbon, counting from the same end of the molecule, means we'll put a methyl branch here. Now just a word about the bond angles in alkenes. Remember that when carbon has 4 bonds, if you have carbon with 4 bonds, what you get, I'm going to draw this in 3 dimensions. Let me do it a bit differently here. So in this representation, here's a methane molecule. That carbon atom and those 2 hydrogen atoms, think of all 3 of those atoms as being in the plane of the paper. So the bonds there are in the plane of the paper, so are the 3 atoms. Another atom in methane, I'm going to draw an open wedge to represent its bond. This open wedge, you have to imagine, is coming out of the paper towards you. So this is meant to communicate 3 dimensions. So this open wedge is a bond coming out of the paper towards you. And there's another hydrogen atom. And then the 4th atom in methane, I'm going to draw another wedge, but this time it's going to be a dashed wedge. And where the first wedge was pointed at the carbon and opened outwards towards the hydrogen, the dashed wedge is wider at the carbon and gets narrower as you're going away. That dashed wedge is meant to mean the bond is going away from you. It's going behind the paper. So this is to communicate 3-dimensional geometry. The bonds which are just lines are bonds that are in the plane of the paper, and the atoms there, the H at the top, the H on the right, and the carbon would all be in the plane of the paper. And then the open wedge is coming out of the paper towards you, and the H that's there is coming towards you. The dashed line is going away from you behind the paper, and the H there is behind the paper. So that's meant to communicate a tetrahedral geometry, and the bond angle there is 109.5 degrees. Now if you have an alkene, something strange happens. The geometry changes. In an alkene, I'll draw this carbon and I'll put 2 hydrogen atoms here. So if you followed my description earlier, you know these are all in the same plane. The bonds, the atoms are all in the plane of the paper. Then I'm going to draw a double bond over here, and notice by drawing it like this, it means it's in the plane of the paper. So I can attach another carbon atom. So these atoms, all 4 of them, and the bonds are all flat in the plane of the paper. And the bond angles are no longer 109.5 degrees. Each of these bond angles is 120 degrees. They're equal, even though I didn't quite sketch it accurately, and they are 120 degrees apart. So that's what happens in an alkene. So when you look at the molecule we drew a moment ago, you can label this angle is a 120 degree angle. This angle is a 120 degrees, as is this angle 120, as is this angle 120. That's because those carbon atoms at the vertex of each angle are involved in double bonds. But the angle over here is there's no double bond at that carbon, so that would be a 109.5 degree angle. That's the tetrahedral angle. All right? Okay, let's do one more or a couple more of these, D and E. See if you can draw that molecule yourself. So 2-butene, I'll start with a double bond, the ene. But is telling me there's going to be 4 carbons in the molecule's main parent chain. So far I've got 2 of the carbons here. 2-butene is telling me that the double bond is the second bond in the molecule. So I'll attach a carbon here and I'll attach a carbon here. If you're watching this video and you've studied some cis-trans geometry, cis-trans isomerism, we're not going to be discussing that in this video at all. So if you're thinking about cis and trans isomerism, that's not going to be addressed here. And now 2-chloro. We haven't seen chloro before. When a halogen, chlorine, bromine, fluorine, iodine, when those are attached to hydrocarbons, they're called chloro, fluoro, bromo, and iodo. So here, when we see 2-chloro, it means there's a chlorine atom attached to the second carbon in the molecule. So it's a branch, and it's on the second carbon, there's a chlorine atom. On the third carbon, there's a methyl branch. So there is 2-chloro, 3-methyl-bute-2-ene, or the American system, 2-butene. See if you can do this next one yourself. So again, I start with my double bond, octene. It's got 8 carbons in the parent chain, and I've already got 2 here. The third bond is the double bond. So let's put the carbon here and a carbon here. So this would be the third bond in the chain. The first, the second, the third bond is the double bond. But I've used 1, 2, 3, 4 carbon atoms. So I need another 4 atoms of carbon. So let's go up, 1, 2, 3, 4. Just double check, 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5, 6, 7, 8. That's the 8 carbon atoms in the parent chain, and the third bond in the parent chain is the double bond. So far I've got 3-octene, or oct-3-ene. Now let's put the branches on. Notice that they're put alphabetically. Chloro comes first, ethyl, and then fluoro. Remember, when you're alphabetizing, you don't look at the prefix di, you just look at chloro. So chloro comes first, then ethyl, then fluoro in the name. 2,2-dichloro means on the second carbon, counting from the same end of the molecule that we did for the double bond, has 2 chlorine atoms. 5-ethyl, the fifth carbon, 1, 2, 3, 4, 5, has an ethyl branch with 2 carbons. And the sixth carbon has a fluorine atom, fluoro. So there's the molecule. All right, let's jump ahead to some alkynes. Here's some alkynes, which have triple bonds. All right, now interesting geometry around alkynes is that the bond angles here are all going to, when there's a triple bond involved, are going to be 180 degrees. Okay, with triple bonds, the bond angle is 180 degrees at the carbon where the triple bond is found. So these 2 bonds are 180 degrees. Remember, there's a carbon here and there's a carbon here. So since I've started talking about part D, can you come up with this guy's name? Well, the parent chain has 1, 2, 3, 4, 5, 6 carbons. And we need to tell you where the triple bond is. So it's the first, second, third bond, whichever end you count from. It'll be the third bond. So with 6 carbons, and the third bond is a triple bond, this guy's name will be hex-3-ine, using the UPAC nomenclature, or 3-hexyne, using the American system. Its chemical formula is going to be C6. Now, if it were an alkane, it would be H14. But we've got 2 extra bonds. To make a triple bond, we have 2 extra bonds. So therefore, we have to take away 4 hydrogen atoms. So instead of CnH2n plus 2, we get CnH2n minus 2 as the formula of an alkyne. So this guy's formula, 2 times 6 is 12, take away 2 is 10, C6H10. If you want to prove that to yourself, this carbon would have 2 hydrogens attached, this carbon would have 2 hydrogens attached, this carbon and this carbon already have 4 bonds, so they don't get any hydrogen atoms. So there's going to be 3 plus 2 is 5, plus another 5, there are 10 hydrogen atoms in that molecule. Try part G, see if you can do this guy. Pause the video and give it a try. So the parent chain, the longest chain, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 atoms in the parent chain. It's an alkyne, a triple bond, so it's going to be no 9 as the parent. Now, which end should I number from, the left or the right? Well, the answer is whichever end is closer to the triple bond. So in this case, we'll count from the right. Then it's not the first, it's not the second, it's not the third, it's the 4th bond, which is the triple bond. So therefore, we're thinking known 4-ine as the parent root. But we have these branches. The branches, we look at the carbon atoms and we number from the same end. So from the carbon atoms perspective, this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. So therefore we can see that carbon 2 has a methyl branch, while carbon 6 has an ethyl branch. And we name those branches alphabetically, so we put the ethyl first. So this will be 6-ethyl dash 2-methyl known 4-ine. That would be the UPAC way of doing it. The American system would say 6-ethyl 2-methyl, and then they'd say 4-nonine. The chemical formula, nonine has 9 carbons, plus a methyl is 10 carbons, plus an ethyl is 12 carbons, so C12. And then the H's would be 2N minus 2, so 2 times 12 is 24. Take away 2, C12H22. All right, I'm going to stop there. That should give you a good head start. For homework tonight, try to get up to question 16 done. All right, so try to do up to 16 before Wednesday's class.